So, in case of ADC, analog to digital converter, so there are several errors that can come up. So, two major error are the aliasing error and quantization error. So, aliasing error or sampling error, so this occurs when the input signal is changing much faster than the sampling rate. So, we have seen previously while discussing on sample and hold circuit that the sampling rate should be sufficiently high, so that signal can be reconstructed at the receiving end. So, here also when we are converting one analog signal to digital signal, the sampling rate should be sufficiently high, so that we have enough information about the signal, and later on when that digital signal is processed. So, this digital signal is having enough information about the analog signal, so that later reconstruction may be possible. So, there is a theorem called Nyquist rule which is to be followed for this sampling. So, this sampling in Nyquist rule, so it answers question of what sample rate is required. So, it is required that a sampling frequency should be at least twice as high as the maximum frequency in the signal to avoid aliasing. So, maximum frequency of a signal in a signal means in the analog signal, for example, if there is a say music that is playing. So, there are several frequencies that are there. So, if you want to get a true picture about the music, so you have to find out what is the maximum frequency in that music, and the sampling rate should be twice that of the highest frequency. So, if we do not do that, so there will be aliasing. So, later on the reconstruction may be problematic. So, you may not get the original signal back in its true form. So, the third point here is actually telling us that what is the formula. So, this one the sampling frequency should be twice the signal frequency, or you can say the maximum frequency in the signal. So, this is the aliasing error. Another type of error that can come we have seen in the quantization process. So, quantization, as we have discussed in the last class. So, while converting from analog to digital signal, so we do not have all the levels of analog signals available for to be converted into digital form, and if I have got an n bit ADC, then the number of different digital pattern is 2 to the power n. So, if the total voltage is say V reference, so this V ref divided by 2 to the power n, so many different voltage levels are only possible to be recognized by the analog to digital converter. So, whenever so if these levels are named as L1, L2 up to say L, so this quantity being equal to say K, so this Lk. So, between L1 and L2 there is a change in voltage. So, any signal which lies between L1 and L2, any analog signal, so that is quantized as equal to L1. Similarly, anything lying between L2 and L3 will be quantized as L2. So, naturally it introduces error. So, this error is the quantization error. So, if we want to reduce this quantization error, so we have to increase the resolution. So, if I want that this value of k should be large, then this number of levels should be large. Then what we have to do is that we have to so there are 2 to the in this case there are 2 to the power n levels. So, if we want that to be large, then the value of n should be large. So, as a result this voltage difference, so this is not Lk, so this is L 2 to the power n. So, L1 L2 up to L2 to the power n. So, if I want that I have large number of levels, then this value of n should be sufficiently large. So, that means that this converter will be more complex. So, this is dependent on the ADC converter of the microcontroller. So, very often, so the underlying processor or the microprocessor or microcontroller, so they have got built in ADC, and this ADC for the ADC the resolution is fixed. So, you cannot change it. So, error is dependent on that. So, these are the two sources of error in case of ADC. Applications. So, ADCs are used virtually everywhere where an analog signal has to be processed, stored or transported in digital form, like microphones, strain gauges, thermocouple, digital multimeter. So, everywhere you will find some application of ADC. So, ADC. So, next we will be looking to different types of ADCs that are available. So, of course, this list is not exhaustive. So, in fact, this analog to digital converter design by itself is a research area. So, there so even you can today you can find lots of research papers on this analog to digital converters, but the purpose of this course is to understand the basic analog to digital converter designs. So, we will be looking into 3 alternative designs. One is known as successive approximation AD converter, another is flash type AD converter, another is dual slope AD converter. So, successive approximation AD converter, so this is a serial converter. So, this will try to approximate, it will try to guess like what is the value of the analog signal. Accordingly, it will set some bits, and then if the signal value is higher than the guessed value, then we will be further turning on some more bits. So, it will go like this. We will see how this is done. So, in a step by step fashion, so if there are say n bit for an n bit ADC, so it will be doing in n steps by setting and resetting the bits. On the other hand, this flash type ADCs, they are pretty fast. So, they are so this it uses a number of comparators, and these comparators they work in parallel, and accordingly this flash ADC will be setting this comparator outputs to high, such that we can get the corresponding digital bit pattern to understand like what is the corresponding digital value. And this dual slope AD converter, so this uses some reference signal, and with respect to that it tries to see like what is the amount of what is the level of the given analog signal. So, that way it is doing a dual slope AD converter. So, we will see them one after the other. The first one is the successive approximation AD converter. So, here what we have is that, so this is there is a successive approximation register, this SAR. So, the SAR stands for successive approximation register. So, this successive approximation register, so if I have got an n bit ADC, then the size of this successive approximation register is also n. So, interestingly, it uses one digital to analog converter as a module in this ADC. So, while designing this ADC, we need a DAC to be implemented, DAC to be available. So, there are a few signals, like clock signal means that in every clock, so it will be doing some operation. So, this SAR register, so it has got a clock, so that at every clock output at the clock active point, so the bit pattern will be available on these lines. There is an end of conversion signal or EOC. So, this tells the outside world that the conversion is over. And also we have got a sample and hold circuit. So, this sample and hold circuit, the input signal is applied here. So, this will be sampled, the value will be sampled and held for some time. It will be doing a comparison, and then the comparator output will be fed to this SAR, so that the SAR will be changing the bits. So, we will see it how it changes. Now, after n such steps, this EOC signal becomes high, telling the outside world that for this current sample the conversion is over. So, whatever be the value of this D0 to Dn minus 1, so that gives me the digital equivalent of the analog input signal V in fed here. So, we have got this DAC, which is the digital to analog converter, end of conversion signal, successive approximation register SAR, the sample and hold circuit SH, input voltage V in, a comparator and a reference voltage. So, this comparator is simply an operational amplifier which is connected in open loop configuration, and you see that if this signal is more than the output from the DAC is more than V in, then this will be high, this will go to plus VCC. So, if we assume that this has got supply voltage of connected to VCC and VCC and ground, then what will happen is that, so when this value is higher than this, then the output will be high, and later on when this V in becomes less than V in becomes higher than this DAC output, then it will become low. So, that way this is a comparator that works in this operational amplifier that gives only 2 levels of output, plus VCC and ground. Okay. So, that is the and Vref is the reference voltage. So, how does it operate? So, let us try to understand. So, this SAR successive approximation type ADC, it uses an n bit DAC and original analog results, and it performs a binary comparison between V voltage coming out from DAC, VDAC and V in. So, this is the VDAC coming out of the digital to analog converter. So, this is the VDAC and V in, they are compared, and then this is compared. So, VDAC is compared with V in. Initially the most significant bit is initialized to 1 for the DAC. So, this successive approximation register, what is done is that the most significant bit, that is Dn minus 1, is set to 1 and rest of the bits are set to 0. As a result, this DAC will be outputting a voltage which is equal to Vref by 2. So, this Vref by 2 is compared with V in, and if V in is higher than Vref by 2, that means this output will be this comparison output in that case. So, if V in is less than VDAC divided by Vref by 2 to the power n minus 2 to the power 1, that is Vref n equal to 1. So, then MSB is reset to 0. So, if V in is less, that means the value that we have guessed through this successive approximation register, that voltage value is higher than the V in value. So, as a result, in the digital count, the MSB should not be 1, so it should be 0. So, MSB is reset to 0. On the other hand, if V in happens to be greater than VDAC, which is in this case it is n equal to 1. So, actually if this comparison fails, if V in is not less than VDAC. So, this is a bit confusing here. So, we should better say that if V in is greater than VDAC, where n equal to 1, So, that means in this previously we have set this MSB to be equal to 1 in the SAR register and all other bits were 0. So, with that we have got the output from this DAC, which is Vref by 2, Now, if this V in happens to be more than Vref by 2, that is the second condition, this condition is true. So, this bit must continue as 1. Now, I have to try to set this bit. Okay. So, that is what is done. So, if V in is greater than VDAC, then successive bit is set to 1. So, this bit I try with setting equal to 1. Now, these two bits being 1, so VDAC value will be even higher, and then again the comparison will be done. So, if now it happens that this is less, in that case this will be reset to 0 and then this will be turned to 1. So, it will go like this. On the other hand, if it is if the initial point itself V in is less than VDAC, so this bit is reset to 0 and we set this second bit to 1 and it proceeds like this. So, this way the algorithm is repeated till the least significant bit position. At the end, DAC input equal to ADC output. So, the ADC output is that one, and this for n bit we need some n comparison cycles for this purpose. So, this way this conversion takes place. So, we have got an example that will tell how this is going to happen. Suppose we have got a 5 bit ADC with V in equal to 0.6 volt, the analog voltage value is 0.6 volt and Vref reference voltage is 1 volt. So, in the first cycle MSB is set to 1. So, this is the 5 bit pattern that we have. So, this is the 5 bit pattern that we have. So, there this MSB is set to 1. So, Vref the VDAC value is Vref divided by 2, that is 0.5. So, when we compare 0.5 and 0.6, so V in is greater than VDAC. So, as a result the successive approximation register content remains unchanged. In the second cycle, this SAR, the second bit of the SAR is set. So, it becomes 11000. So, for DAC bit per voltage. So, if you for every bit, so in this table we have listed the voltage value, corresponding voltage value. So, in cycle 2, when these two bits are set, so 0.5 plus 0.25, so that will be the VDAC output, so that is 0.75. So, 0.75 is more than 0.6 volt. So, in this case V in is less than VDAC, as a result this bit will be reset. So, the DAC content becomes like this, SAR content becomes like this. Then we come to the third bit. So, third bit is turned 1 and third bit's contribution is 0.125. So, 0.125 is added, so it becomes 0.625. Again V in happens to be less than VDAC. So, this bit will be reset. So, we again remain at this position. In the cycle 4, we will be trying out the fourth bit. So, this bit is turned 1 and then so the contribution is 0.0625. So, it becomes 0.5625. So, 0.5625 is less than V in. So, V in is greater than VDAC. So, this bit survives. So, this bit remains as 1. In the fifth cycle, so we turn on the LSB and then the contribution is added. So, the value becomes 0.59375 and since V in is greater than VDAC. So, this bit remains unchanged. So, this bit remains 1 only. So, this way through this through an iterative step. So, every individual bits from the MSB side is turned on and then if the content becomes, if the DAC output becomes more than the input voltage, then the bit is reset. If the input, if the DAC output is less than this input voltage, then the bit is retained to 1. Of course, for equal, if the V in and this reference this VDAC, so these two are equal, then also we have to retain the value, and in fact, in that case we do not need to proceed with further bits, rest of the bits will always be 0. But anyway, so that is not shown here as a case, but you can always do that exercise. At any point of time V in becoming equal to VDAC, whatever be the SAR content, so that is the digital output, and we can terminate the conversion process there, though it is difficult to detect that situation. So, normally we do for all the n cycles and take the DAC output after n cycles only. So, next we will be looking into flash type ADC. So, in flash type ADC, so as the name suggests, the conversion is done in a flash. So, all the bits are set simultaneously and this is a parallel type of ADC. So, the elements that we have here is encoder that will convert output to of comparators to binary, and we have got a set of comparators. So, any comparator is like this. So, if this is a comparator circuit, so you see this V1 and V2, so these two are input to the comparator, and so it has got Vs plus and Vs minus as the supply voltages. So, this is Vs plus and V saturation plus and V saturation minus, we tell that way. So, if this V1 is greater than V2, then this V out is equal to Vs plus. If V1 is less than V2, then V out is equal to Vs minus. So, that is, this is basically logic high and this is logic low. So, these are the two things. Now, what is done? The we apply some, so this is the encoder circuit. So, encoder circuit, so it is an 8:3 encoder. So, if you give an 8-bit pattern here, so it will be converted into 3-bit binary output. So, we will see how it operates. So, in case of flash type ADC, what is done? We have got a number of comparators. Okay. So, this is an 8-bit ADC. So, this V in value lies bit. So, V in, so you see, if you look into the circuit, so this is the reference voltage V star, and from this, so we have got a series of resistances. So, we have connected 8 such resistance, 1, 2, 3, 4, 5, 6, 7, 8 resistances. So, if you try to measure the voltage at this point, so this is equal to 1/8 V, 1/8 of this V star. Similarly, at this point, so this is 2/8 of V star, that is 1/4 of V star. So, this point is 3/8 of V star, like that. So, this V star voltage, the reference voltage, we have divided into a number of intermediary values, 1/8 V, 1/4 V, 3/8 V up to 7/8 V. And the input voltage is applied to all these comparators simultaneously, and this voltage is also applied. So, this first this comparator, this is for the LSB. So, this will be doing a comparison. So, depending upon the voltage value that you have given, Vi value that you have given. So, this comparator output may be 0 or 1 depending upon the voltage, whether the voltage is more than the voltage that we are getting here. So, if the Vi is greater than this 1/8 V star, then this bit will be set to 1. Similarly, at this point, if it is more than 1/4 V star, then all this bit is also set to 1. So, it may so happen that at this point it becomes low, V in becomes low. So, this becomes 0. So, rest of the bits are 1 and all these bits will be 0 from that point onward. So, then it goes into a priority encoder. So, priority encoder, it will see that these 3 bits are 1. So, accordingly it will be doing an encoding and it will be producing a 3 bit output. So, so how many bits are 1? So, this significant 3 bits are 1. So, you can say the count value that we have is basically so this is so if you think in terms of count values. So, the initial the first count value is 0 0 0 0 0. So, that is outputted as 3 zeros, then 0 0 0 0 1. So, that will be outputted as 0 0 1, then 0 0 0 0, then so it the 1 will start at some point and then it will continue. So, if you get after that if you get the pattern which is 2 ones. So, this is 2, output will be 0 1 0 and the example that we have taken. So, here it is 1 1 1. So, this then this bit is the bit before that is 0. So, this is coded as 3. So, it will be coded as 0 1 1. So, this basically counts. So, at this at this output of these comparators. So, we have got the count value, but in some unary number system you can say. So, it can produce all 0 to all 1, but the pattern that it can produce is 0 0 0 0 0 0 0 0, then 0 0 0 0 0 0 0 1, then 0 0 0 0 0 0 1 1, then 0 0 0 0 0 1 1 1. So, it can go like this. Okay. So, this 1. So, once a bit becomes 1, the bits towards the right of it must be 1 and the bits towards the left of it must be 0. So, it is important to find out where how many ones are there. So, accordingly this priority encoder circuit, it can do the it can do a encoding and output the corresponding sequence number. So, in this particular example we have got Vref equal to 8 volt and a 3 bit encoder. So, resolution is given by 8 by 2 to the power 3, that is 1 volt. Okay. So, number of comparators needed is 2 to the power n minus 1. So, that is 2 to the power 3 minus 1, that is 7. So, we need 7 such comparators and so one additional encoder bit will be. So, if we say that okay, instead of 3 bit instead of having 3 bit ADC, we will design a 4 bit ADC, then the number of encoders will become 16. So, every additional encoder bit, number of comparators will double. So, that is the cost of flash ADC. So, the number of comparators needed is pretty high, but this conversion is immediate. So, this whenever this input is given, accordingly this unary pattern will be set here and this priority encoder will encode it into one of the binary pattern. So, that way this flash ADC works. So, another example, suppose V in equal to 5.5 volt and Vref equal to 8 volt. So, V in lies, so 5.5 volt. So, V in will lie between become 5 and 6. Okay. So, this is so the bit pattern will be like this. So, this is between 5 and 6. So, up to this so this 7th and 8th bit. So, they or 6th and 7th bit. So, they will be 0 and the up to bit number 5 they are all 1. So, then because Vcom 5 is Vref into 5 by 8, that is 5 volt, and Vcom 6 is Vref into 6 by 8, that is 6 volt. So, comparator 1 to 5 will be equal to 1, comparator 6 to 7 will be equal to 0. So, this is the unary coding that I get. So, 0 0 1 1 1. So, there are 5 ones in it. So, the binary output of this priority encoder is 1 0 1. So, that is the operation of the flash ADC. Now, next we will be looking into another analog to digital converter, which is known as dual slope analog to digital converter or dual slope ADC. So, basically the circuit is like this. So, there is a reference voltage and this ADC is this capacitor is charged for some time and then it is connected to this supply voltage and this input signal, and then we try to see in comparison to this how much time this capacitor needs to get discharged or charged. So, like that. So, I will explain it how does it work. So, an unknown input voltage is applied to the input of the integrator and allowed to ramp for a fixed amount of time Tu. So, initially the input voltage, the V in is the input voltage. So, it is connected to this, and this circuit is kept on for some amount of time. So, that is controlled by this control logic. So, this gives this start and stop pulses. So, this control logic will be telling the we will be noting down the time, and for Tu amount of time this switch remains in this position. As a result, this integrator output, so this is an integrator configuration. So, integrator output will be increasing like this. So, integrator output increases like this. So, it is charged, it is allowed to ramp for a fixed amount of time Tu. Then a known reference voltage of opposite polarity is applied to the integrator and is allowed to ramp until the integrator output returns to 0. So, at this point what is done? So, at this point this switch is taken down to the Vref position, and it is ensured that the polarity of Vref is the inverse of polarity of Vin. Then when you do this, so capacitor will start discharging. Okay. So, because this is a negative voltage, so it will, if the Vin is positive, Vref is negative, so it will start discharging. So, we see the depending upon the value of Vref, so and the amount of charge this capacitor has, so it will take some amount of time to get discharged. So, this is happening here, that a known reference voltage of opposite polarity is applied to the integrator and is allowed to ramp until the integrator output returns to 0. So, this is the time Td. The input voltage is computed as a function of the reference voltage, the constant run up time period and the measured run down time period. So, these values are, so how is it computed? So, V in is then given by minus of Vref into Td by Tu. So, minus comes because V in and Vref are of opposite polarity, and this Td by Tu. So, this ratio will tell me what is the ratio between Vref and V in. So, that is how we measure the input voltage. So, this rundown time measurement is usually made in units of converter clocks. So, longer integration times will allow higher resolution. So, then what is happening is that we in this circuit we have got a counter. So, we count the amount of time for which it has to come down. So, the time needed for Td time is fixed, the counter value will be fixed, the Tu time will be computed by looking into this counter when this capacitor is discharging, and then this Td Tu ratio will be computed by this control logic, and it will be telling the what is the corresponding bit pattern. So, that part is not explicitly shown, this control logic will finally output the bit pattern depending upon this Td Tu ratio. So, if you compare between the ADCs, then these dual slope ADCs are a bit slow, flash ADCs are very fast, and successive approximation are medium fast. Cost, dual slope medium cost, flash ADC high cost, and this successive approximation is low cost. Resolution, dual slope is 12 to 16 bit, flash ADC is 4 to 12 bit, and successive approximation 8 to 16 bit.